Optimization. Using our techniques for finding the maximum and minimum values for a given function, we can solve applied optimization problems. These are going to be the steps that we're going to follow. Step 1. Make sure you read and fully understand the problem. Step 2. Draw a diagram of the situation if it's possible and label all given and required quantities. Step 3. Create a function that represents the quantity to be optimized. This is going to be the one that is going to be maximized or minimized, the one that we're going to differentiate. Generally, we will want this function to only have two variables. Step 4, figure out the domain of the function to be optimized. There will be ranges that we might get, or answers that we might get that are going to be outside of possible answers. So we want to know what's going to be not possible. Step 5, use the procedure for determining the absolute maximum or minimum for a function on the closed interval, and then state the solution to the problem. So let's see what this looks like. Determine the maximum area that can be enclosed by a rectangular shape with a fixed perimeter of A, 50 meters, and then B, just P meters in general. So we're always going to end up with two possible, two formulas. Okay, so we have two things that are working together. We have a formula for area, which is length times width. And we have a formula for perimeter, which is 2 lengths plus 2 widths. We're given some more information about the perimeter, that this needs to equal 50, and we're told that we want to maximize the area. And because we want to maximize the area, this is the one that we're going to differentiate. Now we can't take the derivative of this until we get rid of one of these two variables. There's just too many things here. So we're going to rearrange this equation, and we'll say that 2 L plus W equals 50, or L plus W equals 25, or W equals 25, take away L. Then we're going to take this definition of perimeter and plug it into the W spot over here. Now I can write area as a function of length times 25 minus the length. And I can solve this so that I have 25L minus L squared. Now that I have only one variable over here, it's much easier to take the derivative. So I want to take the derivative of A with respect to L. I want to find the optimal or the max or the min here. So I'm going to set this equal to 0 and rearrange to see that the length of this rectangle must be 12.5. Let's talk about what we're doing in general. So in general, we knew that the perimeter needed to be 2L plus 2W, or 2L plus W. And in general, we knew that the area needed to be length times width. So let's say we don't know what the perimeter given is. We'll rearrange to still solve for W, but instead of knowing the value of the perimeter, we're just going to have the perimeter divided by 2 minus L. And we're going to plug this into our area formula because this is still the one that needs to be maximized. So we're still going to use this formula. And we're going to have area equals length times perimeter divided by 2 minus length. Okay, now I'm going to take the derivative of this, derivative of A with respect to L. So I'm going to end up with P divided by 2 minus 2L. Set it equal to 0. Rearrange to solve. And I'll see that the maximum area is going to be given when the perimeter is divided by 4 for a side length. In other words, when we get a square. try another example. A piece of sheet metal that's 60 by 30 is used to make a rectangular box with an open top that's made by cutting a square out from each corner and folding the edge up. So let's draw a diagram first. And so I'm going to cut out a square from each of these corners. And then I'm going to make a fold. I'm going to fold this edge up and I'm going to throw away this material here. And this needs to be, this is going to represent the height of the box. Okay. This is 60 and this is 30. So the dimensions of the box, let X represent height. The width is 60, take away the two heights, and the length is 30, take away the two lengths, or two heights. Okay, so I am looking for the maximum volume. So volume equals length times width times height. And in this case, I've got 30 minus 2x, 60 minus 2x, and then just x. I'm going to multiply this out. So I'm going to get 30 times 60 is 1800 times by x. 30 times negative 2, 2 times 60, and negative 2 times negative 2. And I multiplied that x in at the same time. Okay, combine my like terms. And now I can take the derivative because I want to find the maximum. Sorry, 180 times 2. Set it equal to 0, and I can factor out that 12. 1800 divided by 12 is 15. Sorry, need the 0 there. So I got 150 here. And now I can find out when this is true. This is not going to be a whole answer. So I'm going to use my quadratic formula to solve. So I have, oh, sorry, and I missed a 0 over here. So hang on. Okay, so I'm going to have negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. And I'm going to put that in my calculator. I'm going to get two potential answers. One answer is 6.34, and one answer is 23.7. Now, if I look at the maximum value over here, and I should have done this before, so the possible range for x, well, x has to definitely be a whole number or a positive number, and x can't be bigger than 15 because my maximum size here is 30, and so I can't cut up a side and still create a box if it's bigger than 15. That's going to mean that this is an inadmissible answer, and so my final x is going to be 6.34. And then I can use these expressions to figure out that the dimensions of the box is 6.34 by 47.32 by 17.32. All right, let's try a different context. Let's say we have a parabola, x squared plus 2. So there's 2. Here's my y equals x squared plus 2. And I want to find the points on the parabola closest to the point 0, 5. So this point up here. So that's going to actually happen twice. So I'm looking for 2 solutions. And it's actually going to, let's zoom in here. It's actually going to follow Pythagorean theorem. And I'm going to get, this is going to be my distance right here that I'm looking for. Okay, so the distance between these points squared is equal to the difference between the y points, the change in y, and the change in x. Okay, so we're using this formula, if you remember from grade 10, x1 minus x2 squared plus y1 minus y2 squared. Okay, I'm already given this point here, which is 0, 5. So I'm going to just plug that in here. So x minus 0 squared plus y minus 5 squared. Now, I don't want to use y because that's too many variables. So I want to think about what the value of y is right here. So this point is going to be x, and then whatever, and then I'm going to use this expression for y here. So x squared plus 2. So I'm going to use this definition of y in here. Okay, so d squared equals x squared plus x squared plus 2 minus 5 all squared. Okay, now that I have that, I'm going to keep simplifying this. X squared plus 3 all squared is going to give me x to the power of 4 plus 3x squared plus 3x squared plus 9. Combining my like terms, I'm going to have, sorry, I missed a negative here. Okay, so this needs to be a negative 3, and this needs to be a negative 3. Okay, so I have x to the power of 4. I have x squared minus 3x squared minus 3x squared is going to be minus 5x squared plus 9. Now I have an expression that's ready to be differentiated. So the derivative of d squared with respect to dx will be 4x3 minus 10x. And I can set this equal to 0. Look for some of my answers. Okay, so I know this is true a couple of times. So I know this is true when x is equal to 0, and I know this is true when x is equal to positive or negative 5 over 2, root 5 over 2. Okay, let's draw a graph just so we can see a graph of the derivative. So I'm graphing this guy right here. Okay, so I have these 3 roots. I have an answer at 0. I have an answer at negative 5 over 2. And I have an answer at positive 5 over 2. And this function is a cubic function with a positive first term. So I'm going to start in this quadrant. I'm going to go up, down, and up. Okay, so when I am going from a negative to a positive, that gives me a minimum.